So a step up from simplifying is something that we call verifying trig identities. So just taking an equation, something like this, and trying to show that one side of the equation actually does equal the other side of the equation for any value of x. So kind of like our trig identities that we looked at earlier, but more complicated. And so trying to use our simple identities to prove a more complicated identity. So we've got some different hints here. Definitely we're working with one side of the equation. So we're always trying to choose, okay, on this first one, and it said using the more complex. So we might look at this left side and say, okay, I can actually do more with this. It looks like maybe I can factor some things out. Whereas if I start with the already kind of simplified, it's a little trickier to know what to start with. So pick one side of it. We're looking for things that we can factor. We can add fractions, square a binomial, create a monomial, looking for using those fundamental identities. So can I write everything in terms of sine and cosine? Can I use a Pythagorean identity, something like that? Which that's actually step number 4. If that doesn't work, turning it into sine and cosine. And then definitely trying something is a big deal here. These don't always work. I'm not going to give you a ton on the homework. I just want you to try a few of these. But definitely if you try something and it doesn't work, that's okay. You just start over and try something different. So starting with number 14, and this is from the textbook, by the way, so this is number 14 from the textbook. Like we said before, starting with that left side because it is a little bit more complicated. And then I just want to go with my gut on doing something with the identities and seeing if I can manipulate it to where it ends up being that right side. So I might notice that there's a secant tangent in both. They also both have this secant at least raised to the 4th. So I'm going to try starting with that left side, and I'm going to take out a secant to the 4th and a secant tangent. So technically I've taken out a secant to the 5th, but anyhow. I'm left with my secant squared in that first part. And then in the second part, I'm just left with -1. So I took out that whole thing. And so if I want to simplify this left side of it, I can go ahead and say secant to the 5th times tangent. This piece, hopefully I'm starting to recognize those Pythagorean identities, that since it has that trig function squared and a -1, that it's going to be using one of those trig identities. And if you'll look back at your trig identities, see if you can tell what is going to go in that blank. So hopefully you decided to replace that secant squared x -1 with a tangent squared. Again, we're just looking at that second Pythagorean identity and deciding, okay, if I have that secant squared and I've subtracted 1, then on the other side I'm left with a tangent squared. Doesn't hurt to go back to the identities that you wrote down earlier, manipulate it a little bit. Okay, so now we're getting really close, but we want it to look exactly like that other side before we say that we've done it. So my last step here is to go ahead and multiply my tangents to where I have that tangent to the 3rd. And now that it looks exactly, well, it looks kind of funky, but now that it looks exactly like that right side, I'm just going to give it a check to say I did it. I verified that this expression is the exact same as that expression. For our number 16, again, choosing which side of this is more complicated, and definitely the left side is more complicated. This one has more than one way that we can simplify it or verify the identity. And it doesn't necessarily mean that either way that we would simplify this is necessarily better. Sometimes you will choose a direction and it will be a longer route than if you chose something else. But it still is probably best to just go with your gut and to keep working through it unless you really get stuck and can't figure it out that way and then start back at the beginning. But so for this one, I want to show you 2 different ways that you could verify this identity. One way is by writing everything in terms of sine and cosine. So if I write that secant as 1 over cosine, and it seems like at this point that we are stuck, but we have an operation that we can do. I can't subtract 1 and cosine, but up here I could get a common denominator and subtract these two functions. So I'm going to go ahead and multiply this by cosine over cosine. And we can kind of see how this is going to play out, because now my numerator is 1 minus cosine over cosine. And then that was what my denominator was as well, so I'm going to multiply by the reciprocal. Ooh, and not too bad. They're going to cancel. Got 1 over cosine, which remember I'm trying to get to secant. 1 over cosine is secant. Equals secant x. Remember, we just check. We got it. Make sure that at no point you're actually just guessing at what it equals. So I don't want to get at the end here and say 1 over cosine, yeah, I guess that's secant. Make sure that you actually know that it is secant, because that's where it leads to some issues later when you're trying to solve equations rather than just verifying identities. We want to know exactly, I know this is equivalent to something that I'm replacing it with. Okay, so let's look at a different way that we could have verified this identity. And to me, this is what makes identities fun, is that there is more than one way to solve them, because we don't all think the same way. The other way, because we've got this 1 minus cosine in the denominator, is to multiply the top and bottom by the conjugate of that denominator. We've done this before with rationalizing denominators, trying to get radicals or i's out of the denominator, something like that. So by multiplying by the conjugate, and remember that's just the same as this 1 minus cosine, except we've changed the sign in between. That's what a conjugate is. But what's going to happen in the denominator, because these are a difference of squares, or it's going to turn into a difference of squares, when I multiply, I'm going to get 1, then my OI part of the FOIL is going to be a negative cosine and a positive cosine, so those parts will cancel to equal 0, and then I've got this negative cosine times cosine, so a negative cosine squared in the denominator. Notice the Pythagorean triple emerging there. In my numerator, I'm not really sure what's going to happen yet with this, whether I'm going to want to go ahead and multiply it all out or not. So I'm just going to leave it for now, the secant x minus 1 plus cosine. I'm going to see where this takes us. In my denominator, I do have a Pythagorean triple here. So if we remember that sine squared plus cosine squared equals 1, that means we've subtracted the cosine squared over. So that denominator is just sine squared. And it looks like we will have to do something with the numerator. But something that might make this a little bit easier to multiply is if I write that secant as 1 over cosine. I think I would do that eventually anyway, whether you multiply first or if you change it to terms of cosine first. And now when I start to FOIL in the numerator, I'm going to get 1 over cosine. My 1 over cosine times cosine is just 1. I've got a negative 1 and then a negative cosine x. So this would be a great example of it's still going to work out for us, but it is going to be a little bit longer route than what we took in the blue over there. So both going to work though. My 1's are going to subtract to be 0. I notice now that in order to simplify this, I need to go ahead and get a common denominator with my 1 over cosine x and my negative cosine. So if I have my 1 over cosine x and then multiplying this by cosine over cosine, I'm going to get cosine squared over cosine all over sine squared x. And then finally, we can start to notice that this 1 minus cosine squared is the same as sine squared. So if I was going to flip this and multiply, I really have a sine squared x over cosine times 1 over sine squared. Running out of room. My sine squareds cancel, and then I finally have that 1 over cosine, which is secant squared. Whew. So either way, I verified them. In both of them, they're going to have some similar elements. Sometimes you end up even at the same exact step. But these both ended up where I needed that common denominator to subtract. That happened here as well. So some similar elements, but they both worked. So the last example that we're going to look at here, number 50, is a little less intuitive, I think. At first, just deciding which side of this to start with. Really, either side doesn't look any more or less complicated than the other, but my hint to you is that it's typically easier to use the side that has more than one trig function in it, rather than the side that has only one trig function. So we're going to go ahead and start with the left side, the sine to the fourth. And as a direction, I'm going to look at that right side and just say, how could I go from being two different trig functions to only cosines? So typically I can just rewrite things in terms of sine and cosine, but we're really already there. And we're trying to rewrite this sine to where it is in terms of cosine. So a way that I can rewrite this is using that first Pythagorean identity, that if I had sine squareds instead, which this is really just sine squared times sine squared, then I would be allowed to replace it using that Pythagorean identity, sine squared plus cosine squared equals 1. So if sine squared plus cosine squared equals 1, that means if I subtract the sine squared over, then I've got, well, and I'd have to subtract the 1 over as well, I've got a cosine squared minus 1, and a cosine squared minus 1, and plus my cosine to the fourth. Okay, so it looks like maybe we're on our way. Let's go ahead and multiply these out. So I've got a cosine to the fourth. I'm going to have a negative cosine squared, a negative cosine squared, so negative 2 cosine squareds, and then my positive 1. And then my last step, I want to go ahead and combine like terms, but I also want it to look exactly like this. So even though normally we would have the highest power first, that's not how they wrote it. So we're going to go ahead and put the 1 first, our negative 2 cosine squared, and then we've got a positive 2 cosine to the fourth. Okay, so you can't just focus on the one toy, because really your main focus is that you want to be where the people are. So you don't have actual legs. You've got a tail, and you want legs. You want to be where the people are. You're just fixed on this one toy.